Hi everyone, I'm Zenon. Today I'm going to present this paper, FixReverter, a realistic bug injection framework. This work is a joint work with Zach Peterson, Michael Hinks, and Shi Yiwei. So talking about fuzz testing, actually its ultimate goal is to identify vulnerabilities in software. Currently, there is an important question in the fuzzing literature, which is to measure the performance of the fuzzers. So we have roughly 4 different current approaches on doing so. For example, the work FuzzBench is using code coverage to compare different fuzzers. So code coverage is easy to compute, but it is proven to have weak connection with the performance by some existing work. Sometimes different fuzzers are compared with each other by the number of crashes it reported. FL-Semin is a tool provided by FL to deduplicate the results reported by fuzzers. However, this deduplication heuristics are known to be unsound and imprecise. We also have fuzzing benchmarks that use synthetic bugs, for example, Lava. So the synthetic bugs do have clear deduplications, but they're often complained as being not realistic and have problems with overfitting. And lastly, we have some fuzzing benchmarks like Magma, which uses real-world bugs. Real-world bugs are a direct representation of the performance. However, manually injected the realistic bugs into the target program is costly. So with the observations of the current approaches, we identified 4 important goals for a good fuzzing benchmark. They should use relevant real-world benchmark programs. It should contain realistic bugs. It should have a clear deduplication. And it should be able to involve and defend against overfitting. Our proposed solution is FixReverter. So we started by looking at the real-world bug fixes of CVEs and manually summarize Bugfix patterns from them. Those Bugfix patterns would be given as input to FixReverter, which will match the patterns in the source code. And with the match code, FixReverter will revert those codes into injected bugs. This slide shows the overview of FixReverter. So it takes two inputs, a target program, and its Bugfix patterns. First component of FixReverter is called the syntax matcher, which will traverse the program source code and looking for code that matches the definition of the Bugfix patterns. This match code will be used as potential injection site by FixReverter. On the right is the example of the real-world bug fix. So here is the code for the fix, which aids a if check to avoid a downstream null dereference. The syntax matcher will be run on the fixed version of this program and identify this if statement to be a match of one of our fixed patterns. The output of the syntax matcher will be the input of the semantic matcher, whose function is the static reachability and dependence analysis. So firstly, the semantic matcher will detect the reachability of the injection site, like the orange edges all the way down here. And secondly, it will try to find the dependence from the injection site to a potential crash. Following the semantic matcher is the bug injector, which reverts the match code into a potential bug. So for this example, it will be removing the if statement from the fixed version of the code. Last component of FixReverter is the naive bug filter. It runs the injected program with the testing suite and removes any injected bug that is triggered by the suite. And finally, the output of FixReverter is the target program with injected bugs. FixReverter is able to generate fuzzing benchmarks that meet our identified goals. The two-channel FixReverter is scalable on real-world programs, and it injects bugs that match realistic bug fix patterns. The bug injector injects the bug with clear indicators for deprecation, and it is able to involve and defend against overfitting by supporting the development of bug fix patterns. So we manually investigated bug fixes of 800 CVEs and defined the bug fix patterns in 2 vaults. The semantic matcher decides the source code location of the potential injection site, and semantic matcher identifies the relationship. The sentence definition identifies the relationship from the injection site to a potential crash site. In total, we identified 3 bug fix patterns, and the example we went through just now is an example of conditional-abort pattern. So following that is a conditional-execute pattern, which is defined with the existing conditional statement, like if statement here. It involves the addition of a conjunctive Boolean expression, like this condition, symbols not equal to null. And on the semantic definition, the variable being checked in the condition needs to be involved in a downstream dereference that happens within the body of the conditional statement. We also have the conditional-assign pattern, which is the addition of if statement whose body is an assignment to a variable. This variable being assigned needs to have data dependence with the downflow dereference like this. So the bug fix patterns are defined with the context programma, and the sentence matcher of FixReverter would pass this programma while traversing the source code of the program. On the right is the example of the conditional-abort pattern. The sentence matcher, during parsing the grammar, will trace its key variables like the uncompressed buffer variable here. So it will trace the grammar all the way here to the pointer tracer. On the implementation side, the sentence matcher is implemented with clan st, and semantic matcher is implemented with Fuzzer FDS analysis. The key variables traced by the sentence matcher will be given to semantic matcher as an input and used as the 10 sources. The bug injector will revert the conditions with tracers in the match code to inject the bugs. So here, it reverts the condition of symbols not equal to null by removing it. Another thing the bug injector does is to distinguish the states for each injected bug. So when the execution of the input enters a branch that was rejected in the original program, the bug injector will log a message of this injected bug being triggered. Otherwise, it will log it is reached. Noting that the trigger state does not guarantee crashing in the program, and a crashing input of a program may trigger multiple injected bugs. Therefore, there is a triage process by running a failure input with the combinations of the triggered and injected bugs enabled. We define 2 different causes for the injected bugs. When an injected bug itself is able to crash the program, it is called an individual cause. And when 2 or more injected bugs need to be present for the crash, they're called the combination cause. We applied FixReverter on 10 real-world programs and injected nearly 8,000 bugs. We called the resulting fuzzing benchmark the REVBUGBENCH. REVBUGBENCH was integrated with FuzzBench for scalability and reproducibility. So on the evaluation of FixReverter, we ran the evaluation experiment on REVBUGBENCH with 5 fuzzers, each with 24 hours timeout and 3 trials. And here comes with the result of the experiment. On the right is the number of individual causes for the 5 fuzzers growing over time. The x-axis is the time noted in hours. We observed that all 4 fuzzers found actual crashes over 24 hours, and there are over 200 individual causes identified. When comparing across these fuzzers, we found FL++ performed the best, which is in line with some existing study like Magma and FuzzBench. So this supports the claim that FixReverter injects actual bugs. We also observed that after 24 hours, all 5 fuzzers were able to still detect some individual causes. This means some injected bugs by FixReverter are actually challenging for the fuzzers. This slide shows a Venn diagram of the individual bugs for the 5 fuzzers. A large number of injected bugs can be found by most fuzzers, but still, a lot of each fuzzer is able to detect unique bugs. We found that 90% of all individual causes were only found by one fuzzer. So lots of injected bugs are not detected by in this experiment, and actually, FixReverter does not offer such a guarantee. We see this as a trade-off. So if we use any approach that generates input which guarantees the crash of injected bug, a fuzzer that uses the same technology or same approach may overfit on the benchmarks that generated by FixReverter. So in conclusion, we performed a study of real-world bug fixes and identified 3 real-world bug fix patterns. We proposed the approach FixReverter, which injects bugs based on these patterns. And we found that FixReverter is able to inject bugs that are hard to find and cause actual crashes. We have made REVBUGBENCH available at GitHub and also the QR code here. Here concludes my presentation. Thank you.